No, right? Okay, eutectoid transformation is when one solid phase, so austenite is solid, it's already solid, one solid phase transform to another solid phase, which is cementite and ferrite. Okay, one solid phase, which is austenite, transform to cementite and ferrite, which is another two solid phase. So cementite and ferrite, we call it, if someone watch my YouTube videos, my lecture videos, they will know. Cementite and ferrite, we call it, quick, now remember, cementite plus ferrite is
Perlite.
perlite, yes,
Perlite.
perlite. Cementite and ferrite is perlite. So when after this, when I say perlite, it is cementite plus ferrite. Cementite much more, uh, cementite is much more hard. Hard. Ferrite is much more soft. So when we combine, we got a more strong steel. Okay, so in this topic, we want to learn on how does the rate of transformation is it depend on time and temperature? Is it possible to slow down the transformation? And then is this transformation will affect the mechanical properties of the steel? So this is what we're going through in this topic. Okay, so the phase transformation started with a nucleation. Okay, nucleus, if you remember your apa form 5 punya subject, it nucleation. It will start with nucleation. So nuclei is the plural of nucleation, will act as a template on which crystal will grow. So we'll start with nucleation and then the nucleate will grow. So for nucleation to form a rate of addition of atom, nucleus must be faster rate than loss. So once it's been nucleated, and then it will grow until equilibrium is 18. So how to increase the rate of nucleation? We need a driving force. We need something that enhance the nucleation. So what we're going to do is we will increase the delta T, which is the temperature. So here, how to increase it? We do supercooling or superheating. So when I say super, it means very fast. Okay, supercooling means very fast cooling. Superheating means very fast heating. Okay, so supercooling, it's happened in eutectic and eutectoid. Okay, when we want to get a eutectic phase or eutectoid phase, we do supercooling, means that we cool the steel very fast. Okay, or if we want a peritectic phase, we do superheating. You remember what is peritectic? Peritectic is when one, where's the pointer? Okay, when one solid and one liquid, which is at this phase, alpha is solid and the liquid, one solid and one liquid transform to only one solid phase. It called peritectic. To get a peritectic, we do superheating. Okay, a small supercooling, okay, means that small supercooling means that you cool it fast but not too fast. Okay, will result in slow nucleation rate. It will nucleate slowly, and then it will result in only a few nuclei, and the nucleation will growth and form a large crystal because they have a lot of time. They have a time to grow the nucleation because we do cooling slowly. We cool it slowly. Okay, you got a large crystal. Large supercooling means that you cool it very fast will result in rapid rapid nucleation rate. Instead, the nucleus will get a more nucleus. Okay, more nucleus, because you cool it very fast, and then because of the nucleation rate is very fast, you will get many nuclei, and it will result in small crystal, because the period of time is very small, because you do a large supercooling. The crystal cannot grow fast, cannot grow large, apa, that cannot grow lah, cannot grow. So it means that the crystal will be small. How to analogy this situation? I think it's like this. You have a liquid. You have a liquid, and you want to make an ice. Okay, you put in a fridge that have a good fridge, a good performance fridge. Okay, you will get a very fast ice, at 2 hours, example, at 2 hours, or you will get ice. But if you put, that is large supercooling, right? So if you put the liquid, the water, in a fridge that is not good, the freezing is not so good, so it will take more time for the ice to be formed. So that is what is small supercooling and large supercooling meaning. Okay, understand, right? Faham tak?
Faham, madam.
Now, okay, there is two type of nucleation: homogeneous and heterogeneous. Homogeneous nucleation means nucleation is in homogeneous situation lah. It form in the bulk of a liquid metal. Okay, and it require considerable supercooling, high supercooling, which is around 80 to 300. On the other hand, heterogeneous nucleation is much easier, since the you already got a stable nucleating surface. For example, you want to make ice, right? Ice. You make an ice. In your fridge, you already have the mold, right? The mold for an ice. You take out the mold, and the mold itself have, or it's already cool, right? So the mold wall is already effect the time for the ice to be cold. Okay, so the outside of the liquid will solidify first, will nucleate first. Okay, that's why we call it heterogeneous nucleation, because the outside layer of the outside part of the wall, the wall itself already affect the nucleation process. And also impurities in liquid phase. For example, you put something in the liquid, so the impurities will also affect the nucleation. So the nucleation is not homogeneous anymore, it's heterogeneous. And only very slight supercooling. You need only very slight supercooling compared to if you want to make a homogeneous nucleation. Wait, if someone is asking to admit, yeah. Okay. Sorry for the interruption. Next. This is how free energy change happen. Okay, basically we use Gibbs free energy. So this one is not so important. Okay, so solidification. R is the radius of the crystal. Okay, of the crystal. If you want R to increase, okay, you need to reduce delta T. Okay, so delta R decrease as delta T increase. R is the radius of the crystal growth. Okay, if you want the crystal to grow small in small size, okay, you need to increase delta T. Okay. Now, rate of phase transformation. What is the rate of phase transformation? It means that you want to study how fast the austenite to transform to pearlite. How fast? That's why that is what we call kinetic, the reaction rate. uh, Reaction rate, when we call rate, it is usually depend on the times, right? So we want to know the rate of phase transformation of one phase to another phase. Okay. Okay, let's see this one. Okay, so now for example, this is the graph of fraction transform with time. Okay, means that how long the time, what the time required for the transformation to happen. Okay, first at 0, for example, 0 to 5 seconds, nothing happened yet. Here, nothing happened yet. According to this graph, yeah, 0 to 5 seconds, nothing happened, and actually there's something happened, but it's not in. Maybe it is 0.00 something. Okay, the transformation. So this is a nucleation part. Okay, and then you can see the growth part where the transformation is very significant. Okay, we call it sigmoidal. I think this graph we call it sigmoidal graph. Sigmoidal graph. So here you can see at 0 growth, and then at 50%, this one is a maximum rate. Okay, this is the maximum rate. 50%, you can see at, for example, is around 7 seconds. So 7 seconds is the maximum rate where the austenite transform to pearlite, for example. Okay, and here is where the transformation complete. So the rate is start to be reduced until it become constant. Okay, constant means that all the reaction is already completed, the transformation is completed. Okay, this is how you read this graph. Okay, basically we use Avrami equation. Okay, so now you can see at 0.5, 0.5 is the maximum rate, which is at T 0.5. Okay, now the temperature depends on the transformation rate. So you see that different temperature, okay, along this graph, you can see the temperature is reduced, okay, with time. Okay, it means that when you increase the temperature, the reaction rate is very fast. Look at around 7 seconds, or I think 5 seconds. At 5 seconds, the growth, the nucleation, the growth is start to happen. Okay, when you hit your steel at 137, 135. What happened? Okay, and the growth is start earlier, and it's complete also faster, which is around 11 seconds. What happened if you heat your steel at lower temperature, for example 43? Okay, at 43, so the growth will start later, around 100 second, 1000 second. Okay, at 1000 second only, the nucleation start to growth. The process, the growth process is started, and it also will complete later. Okay, complete later compared when you heat it at very high temperature. At high temperature, okay. So rate increases with increasing temperature. Okay. Okay. Now we want to see a transformations and undercooling. What is undercooling? Undercooling is the same term as supercooling. Some people call supercool, some people call undercool, but it is the same. Okay, means that you cool your sample, you cool your materials very fast before it's freezing. Means that at freezing temperature, below freezing temperature. You cool it very fast below the freezing temperature. Okay, so here you can see the temperature and the phase diagram of this steel. Okay, I think you are already familiar with this one. We talked a lot about this last time. Okay, and now we want to focus on the eutectoid transformation. So where is the eutectoid? It's here. Solid, solid, which is austenite, transformed to two other solid phase, which is pearlite, alpha plus cementite, and ferrite plus cementite. So we want to focus at this point. Okay. For the eutectoid transformation to occur, we have to cool it below 7 to 7. So here, at this point, you have to cool it very fast to get this phase. We call it undercool. Okay, undercool. So this is the equation. Okay, and the composition of eutectoid is 0.76. Okay, so now, okay, let's see how the austenite is transferred to pearlite. Okay, so this is austenite. Austenite. You cool it very fast. When you cool it, when your solidification happen, the pearlite is growth. How is growth? Is growth in a lamella structure because of they have two phase, right? Cementite and ferrite. So cementite, ferrite, cementite, ferrite, cementite, ferrite. And it is occurred in diffusion of carbon. Diffusion of carbon. So one phase will go to the another for example, ferrite will diffuse to another ferrite phase because this have a apa ferrite blue kan ferrite will transform to another ferrite phase because this phase is much more rich in ferrite. So diffusion is like that, right? It will go to to the phase that have a rich in that in the same manner, and it will have a carbon diffusion. Okay, carbon diffusion, we call it diffusion process. Okay, so for this transformation rate increase with delta T. Okay, for example here, this is how the percentage of pearlite. Okay, from 0 to 100, this is time. Okay, okay. So when the temperature is at 600, which is delta T larger, you will get that the growth is very fast, which means that at 1 second, the pearlite is already formed compared to when you do supercooling at 675, which is delta T smaller. Okay, so why does it that 600 is delta T larger and 675 is delta T smaller? So you know that T eutectoid is at 7 to 7. Okay, so minus 600 delta T is equals to 1 to 7, right? Okay, compared to 7 to 7 minus 6 to 5. 7 to 7 minus 6 to 5 is equal 102. Okay, this delta T is 102. This delta T is 127. So delta T here is larger compared to here. That is why the supercooling, the growth is much more faster compared to this one. Understand? Okay. If you means that if you do supercooling, is the supercooling form at higher temperature, you will get a cost per light. Okay, which means that cost per light will result in the softer materials. Okay, at lower temperatures, you will get a fine per light. Okay, and it is very the material is very hard. Okay, so here lower temperature 600, at 600 you will get fine per light because the time for the nucleation to happen is very slow, it's very fast, and at 1 second, the nucleus is already growth. So the nucleus is not doesn't have time to grow very far, very big. Okay, so that's why you got a fine per light. Here you got a cost per light because the nucleus have time to grow. Okay, they have time to grow. That's why you got a cost per light. So this one, these materials will be much softer compared to this one. For this one, you will get a more strong materials, and this one will be much soft materials. Okay. And this is important. Okay, so here, how this graph is converted to this graph. So this one, we call it TTT diagram. Temperature, time, transformation diagram. So in the exam, when they say according to the TTT diagram, so if you don't know what is TTT, this is what TTT: temperature, time, transformation. Okay, and we call this one a nose of the graph. Look like a nose, right? Nose, your nose too. Okay, so here from 0 to around 900 seconds, what happened? It is lies in this green line. Okay, in this line, nothing happened. Nothing happened means that not, the austenite is not transformed to perlite yet. That's why we said it's 0% perlite. Okay, green line. Because it is still nothing happened from here 0 to 900. Okay, it's in green line. So as uh, as the time goes by, okay, at 100 second, 100 second, 100 ke? 1000 1000 second, the perlite already, the austenite is already transformed to 50% perlite. Okay, here you can see 50% perlite at 1000, and then you will see that, or it is in the black line. So the black line here is in the middle of green and red line. Okay, the green and red line. The green line is austenite and the red line is perlite. So in the middle, they have 50% perlite. Means that 50% austenite, 50% perlite. Okay, you got what I mean, right? So here, as the time goes by, and the nucleation is complete. So when it's complete, it's 100%. 100% is complete, and then you see this graph is lies in the red line. The red line is 100%, means that all the austenite is already converted to pearlite. Okay. Okay. So basically, in your exam, they will give a condition like this. Okay, austenite to pearlite. Okay, this is austenite. As I say, this is austenite. This is pearlite region. Okay, when you increase the time, when the time increase, the austenite will transform to pearlite as you reduce the temperature, because you cool it, right? You cool it. Okay, so you see begin at T more than 727, which is here, and then you rapidly cool to 625. So where is 625? Is around here. So what you need to do, you do a line from 727 to 625, so the point here. And then what did it say? It said that hold the temperature, when you say hold temperature to 625 constant, and we call it isothermal treatment. Isothermal treatment means that you constant the temperature. Thermal is temperature, right? You constant the temperature at 625. So you just do a straight line at 625, and then it will say that until 1000 seconds. So you stop at 1000 seconds. So what will be the phase at this point? What will be the phase?
Pearlite.
Pearlite, right? Okay. So from austenite, and then it undergo isothermal treatment, the steel will be in pearlite phase. Okay. So here you can see that at green line, there is still austenite because nothing transferred and nothing transformed. So 0%. So the micrograph is like this: austenite. In the middle, there is a 50% pearlite and 50% austenite. So there is still austenite here. And as I said, pearlite, it is the lamella structure because it consists of ferrite and cementite. So you will draw a ferrite and cementite lamella structure like this. And at red one, or all austenite is transformed to pearlite. So no more austenite here in this micrograph, only pearlite, only lamella structure of ferrite and cementite. Easy, right? Okay. It's the same. It's non-eutectoid, means that it's not in this point. It at an pro-eutectoid point. Okay, at the hyper eutectoid composition. If you remember my last lecture, I said that before this point we call it hypoeutectoid. Okay, from this region to below this, hypo. At this point and beyond that, we call it hypereutectoid. So this is non-eutectoid composition. It's the same. Okay, so now we want to learn another phase, which is bainite. So you already know about austenite, right? Austenite is in this region. Okay, along this nose, we call it nose. Look like your nose, right? This is austenite. This is still austenite. Okay, and at this region we call it pearlite. And now we want to learn about bainite. What is bainite? Bainite happen if you cool your material below 627, I think 6 something, 65, no, for 500, 600, I think 650, around 650 at this line, your materials is not pearlite anymore, it's bainite. We call it bainite. So anything that happen in this region, it is bainite. Okay. So bainite is it is still consists of ferrite and cementite, but it it has elongated cementite particle in a ferrite matrix. So this is a graph. This is the micrograph. You can see this is cementite and ferrite. Inside the ferrite there is a cementite particle. So we call it bainite. Okay. It happened in diffusion. It's controlled diffusion. And okay, now you see that at this region is 100% perlite. But if you cool it down below uh, uh, 600, below 600, we'll get bainite. Okay, so no. Okay, but at this point, it's still 50% perlite. Under this point, it is 50% bainite. Okay, when I say 50% bainite, what is the remaining of 50%? What is the phase of the remaining 50%? Anyone? Faham tak? This is 50, this black line kan? This black line is 50% per light. Dia cakap here, it stated that 50% per light from here to here. What is the phase of another 50%?
Austenite.
Okay, yes, austenite. Yeah, another 50% austenite. So here, 50% bainite and 50% austenite. The remaining will be austenite. Okay. Okay, now another term. Okay, we got perlite, we got cementite, ferrite. Just now we learned about bainite. Now the last one I think spherodite. Okay, what is spherodite? Spherodite, as you say, as the name is sphere, means that it is in a sphere shape. Sphere shape. It is a cementite particle in ferrite matrix. Just same like bainite, but it is in the form of a circle, spherodite, sphere. Okay, and it's formed by diffusion. Okay, if you heat bainite just now or perlite at temperature just below eutectoid for a long time. How to get spherodite? You heat bainite or perlite at temperature just below eutectoid for a long time. Okay, and then you get spherodite. There's another term, martensite. So you got perlite, you got ferrite, cementite, austenite. Apa lagi? Spherodite. Now we want to learn about martensite. Martensite is when austenite transfer to martensite. So austenite just now is FCC, right? Face-centered cubic. Face-centered cubic is very ductile, very soft. So if you want your steel to be very, very hard, you do heat treatment, you heat your sample or you cool your sample down to martensite. Martensite is a BCT structure, which is body-centered tetragonal. Okay, this is the crystal structure of the BCT, whereas iron is in the atomic side, in the edge of the cube, and the carbon is in the middle of the cube. Okay, this is martensite. Oh, martensite look like needles. Huh? Just now spherodite, dia bulat-bulat, dia circle. Martensite is like needles. It is within the austenite. So you can see the gray one is austenite and martensite is black one. So from this graph, you can see that, wow, this steel is very hard. Because there's a lot of martensite. So according to the TTT diagram, so martensite is in this region. Because if you want to get a martensite, you have to cool the steel very, very fast. It's rapid. You can see rapid, very fast, from 7 to 7 to 200. So they have no time for perlite to happen, because if you want to get perlite, you need 1,000 seconds. So there's no time for perlite to happen, or no time for bainite to happen. Okay, it's not touch the nose of TTT diagram. It just cool very fast, and you will got martensite here at this region. Okay. Okay. If it say that cool your sample at 200 for 100 second, for 10 second. So you cool it down, or 200 here and then 10 second here. So it is in the region of martensite plus austenite. Okay. And if it said that cool it very fast below 1 second, you will get 100% martensite, because it is in this region. But maybe there's austenite, some austenite in it. Okay, that is martensite. You will get a very, very, very hard steel. Okay, this is the summary. Okay, so austenite, when you do slow cooling, you cool it slowly, steadily, you will get ferrite and cementite, which is perlite. Okay. If you do very fast cooling, we call it quenching, super cooling, very, very fast, you will get martensite. Martensite, which is in BCT structure, body centered tetragonal. What happened if you heat back your martensite, whereas we call it tempering? When you cool martensite, example like this one, right? So you already at here, you already cool your sample, you got martensite. What happened if you heat it back? You cool down again, and then you heat back, you will get bainite. Okay, you will get bainite. You heat it back. Or if you cool it, you heat it more time, higher temperature, for example 600 at 110 power of 5. Okay, you will do a line here, and you will get perlite. Okay, that we call tempering. Tempering. So you get alpha plus cementite, ferrite plus cementite. Okay, tempering. Okay. Okay, so martensite is a single phase. It has BCT crystal structure, and BCT have a few slip planes, so you got a hard and brittle material. So this is the same. Okay, what happened for the phase transformation if you increase, if you add another element, for example chromium, nickel, molybdenum? So still is actually iron and carbon, right? So what happened if you add chromium? What happened if you add nickel, molybdenum, silicon, or manganese? The nose of your TTT diagram will be shifted. So means that the time taken is more. The transformation to happen take more time. Okay, take longer time, because you add more elements. So it will retard austenite to transform to another phase. Okay. Okay. What is this? Okay, this is example. Example, I think in your exam, basically they ask you to predict what will be the phase if you if we give you the process like this. Okay, for example, on the isothermal transformation diagram for 0.5458% carbon iron carbon alloy, sketch and label the time temperature path to produce the following microstructure. Okay, how to get 50% fine perlite and 50% bainite? Let's see, Oh, this is how you calculate. Okay. To get 50% per light and 50% by night, you have to treat it, you have to cool down your sample up to 590. Okay, and then you hold it, you get 50% austenite transformed to fine perlite. Because 590 is not touched by night yet, kan? By night is happen at 580. So at 590 still perlite. Okay, and then you isothermally treat at 470, you cool it down at 470, and it become the remaining austenite will transform to bainite. Okay, this point you cool it at 470 for a long time, you got bainite. Okay, and then you cool it, so you get 50% perlite, 50% bainite. So what is the process if you want to get 100% martensite? So you just rapidly quench to room temperature, you will get 100% martensite. Okay, how to get 50% martensite and 50% austenite? So you cool it down here until 50%, for example, at 400, at 300 degrees, and you hold at this temperature for a long time. Hold at this temperature. So this line, you say that 50% martensite and 50% austenite. That's it. Okay. Understand, right? This graph and how to do a heat treatment for the steel to convert to one phase to another phase. Okay. Okay. This is how the steel the properties of the steel, the mechanical properties is changed with the carbon content. Okay. When you increase a carbon, okay, increase carbon, which is more than 0.76%, you got hypereutectite. Okay, hypereutectite means that more carbon, more hard the materials. Okay, more hard the materials, so you get more hardness, more yield strength. Okay, if you and of course the high hardness will result in low elongation. Okay, so this is the inverse proportional of strength and ductility. Okay, increase carbon content, tensile strength and yield strength increase, but it reduce the elongation. This is the same. How to get fine perlite versus coarse perlite and spheroidite. Okay, fine perlite is much more hard than coarse perlite. Okay, but spheroidite is very hard. Okay, elongation low, more. I mean, fine perlite, fine grain will has lower ductility compared to coarse and spheroidite. So spheroidite is very hard. That's why ductility is very low. Okay, fine perlite, fine structure, fine perlite have more ductility than spheroidite. So, okay. I think, yeah, tempered martensite when you hit, okay, this is, let's see the summary, then you will understand more. Okay, now, as I said before, if you want to get perlite, you cool slowly the austenite. Okay, you got perlite. If you cool moderately, you will get bainite. If you cool rapidly, you will get martensite. And then when you heat martensite, you got tempered martensite. So this is the mechanical properties of this phase. Okay, spheroidite. Okay, sorry, I said before spheroidite is very hard. but spheroidite is very soft actually. Okay, here. Mana tadi? This one. That's why elongation. Spheroidite has very apa? Soft, yeah, compared to fine pearlite. Okay, the softer phase is spheroidite. The hardest phase is martensite. Okay, bainite has a moderate strength. Okay, fine pearlite is much stronger than coarse pearlite. Ductility is the other way around. Spheroidite is very high ductility. Martensite is very strong, so spheroidite is very low, very high kan? Betul lah. Martensite have very along this, the ductility increase. So spheroidite is higher in ductility. Martensite has very low ductility. Okay, it's other way around. Is the material is strong, the ductility is low. Okay, that is all for today. Any question?
No, madam.
No.
Not clear.
Clear?
Clear, madam.
Okay, I will put the assignment in your Google Classroom. But the assignment said assignment 3, but I know you don't have assignment 2 yet, right? So it will be assignment 2. That is based on the topic of phase diagram and phase transformation. I want you to solve all the question, because the question is less or more like your final exam. Okay. I think that's it for today. Haika, can you close this class by reciting wal as?
Sure. Bismillahirrahmanirrahim. والعصر إن الإنسان لفي خسر إلا الذين آمنوا وعملوا الصالحات وتواصوا بالحق وتواصوا بالصبر.
Okay, thank you everyone. If you have any question, just shout in the WhatsApp group. Okay. Thank you. Assalamualaikum.
Thank you, madam.
Thank you, madam.
Thank you, madam.